Hello there again, it's me. Now, I would have liked to pick up on Proposition 7, but either the wording is, either I don't understand the wording, or it's simply in error. Hopefully nothing serious depends on it, but this does not follow from this, unfortunately. This symbol means less. Okay. Well, maybe it does follow. I was reading this as this one less, because we usually rewrite less than signs this way, right? But in fact, it's the other way around, because well, the definition of that symbol says greater than. But it doesn't indicate which side is greater than which in the definition. Maybe it does somehow. Less than. Oh, the one we're seeing is the second symbol, right? Or the first. We're seeing the one with the open end on the left, which is the second symbol, which is less than. Okay, now we usually write less than this way, right? Less. A is less than B, correct? But apparently, in this lingo, I don't know if I have it in my set at the time. G-O less than? It's in my list of symbols. It's been added to my key binding. Now I've got so many of them that they're starting to mess each other up. The geometry less is here, these ones. Oh no, that's subset. It's a square brace. Here it is. Oh no, here. So this is square image of square cup. In any case, it doesn't matter. The point is that if I were to interpret that statement this way, then it's not wrong, right? You see, I was saying, okay, somehow it follows that blue is less than red, right? But it wouldn't follow from that. This would not follow. That if you added something to blue, then it would still be less than red, right? But that's not the way this is worded. And in fact, this doesn't follow from this anyway. So I guess I can go back to this one. All right, let's go back to 27. Not have to miss anything. So I'll save this for later. 7. Now, it's a little tricky to understand this diagram because the other thing that's missing is a definition of the word contour. terminus, conterminus. Okay, maybe that helps, breaking it down. Terminating together, right? Having their things that terminate together, so co-terminating sides, red and red, and blue, at both extremities of the base being equal to each other. Okay. Now, what is being said to be equal to each other? The lines or the triangles? On the same base and on the same side, there cannot be two triangles having their co-terminating red and blue sides. So assume each triangle has a red side and a blue side. At both extremities of the base, so one terminates on this side of the base and one terminates on this side, possibly, and these sides being equal. Well, red and red, and blue. Now, is that defining a triangle or a side? Terminate their commonly terminating sides. I see. Okay, I think I can see a way of interpreting this. Here are two triangles, each having a red side and a blue side. These triangles coincidentally have red sides terminating at the same side of the base and blue sides terminating at the other side of the base. So they are coincident in their terminationness at the base on the same side. And we cannot, according to the theorem, have two such triangles that are equal to each other. These two triangles cannot be equal triangles. Okay, now does that make sense? Does it make intuitive sense that they shouldn't be equal? Well, this dotted line is not given as necessarily flat or anything, right? But that's not part of the problem. The problem concerns two triangles. They could have their vertices anywhere. On the bottom here is another example where the vertices are, offset a little bit to the one side and a little bit up. And in common, both of these sides, and for both of the triangles, if they each have a blue and a red side, their blue and red sides terminate at, respectively, at the extremities of the base. So let's take that as being the definition of the problem. Okay. And see if that makes sense. When two triangles stand on the same base, which they do in fact, right? By virtue of the terminating of their sides on the extremities of the base, and on the same side of it, okay, so we'll consider the top, let's say, first, the vertex of one shall either fall outside of the other triangle or within it, or laying on one of its sides. Okay, that's certainly, as far as I can think of, the only three possibilities, right? Either inside or not inside. Not inside means outside or on one of the sides. And so that follows by prepositional logic. So, if possible, let such triangles be constructed. Consider the top and forget the bottom for the moment. And the statement is that the conterminous sides cannot both be equal. All right. That will have to be the definition, because here they're being set equal, right? So here we've got two triangles with both sides of the triangles themselves being of equal length. Okay, now we know, but maybe has not been demonstrated, I suppose it hasn't, that two triangles having the same length, all same length sides would be, you would be able to place one on top of the other. I thought I'd proven that already. Way back here. Two sides same and similar angle. Oh no, we don't have similar angle though. Okay, so the angles could be different. So here we are, assuming same side, same length sides, but unknown angle. Okay, well, I'll take that as given. So here I've drawn a similar diagram. The two triangles in question, I believe, are these two. And I'll draw, what I'll do is I'll draw little mini ones to reflect, to put on the side, thin ones. And then indicate which is which with an arrow. Okay, that's this one. And here, if I draw it right, it should be completely unambiguous. Whoops. Damn. Still red. So this more or less resembles the second one. How about that? So this one and this one, the assertion is that these reds cannot be equal at the same time as these blues be equal. The reds could be equal, but if they are equal, the blues would have to be unequal. This here is too thick. And I should draw that as another faint line, but it's not really part of the diagram. Alright, now I get to try out my new angle tool. Okay, now I could indicate these angles and show off my angle tool at the same time. Hit that circle. See, I have pi mode now. White. Let's see how it works. How well it works. Ooh, pretty good. See, it made a pie. And this one, no, don't want those. Red. And this one, blue and yellow. Pretty cool, huh? I had trouble with this. I had a funny case of recollection that occurred to me while I was trying to design these pies, and that the whole reason I started making these videos had to do with a problem that I couldn't seem to figure out with pies. And then I realized, oh right, the answer is such and so, and the answer is the same reason I started doing this series. It has to do with a magical number that I'll get to much later on. The solution to the problem that I had, I won't fill them up. The problem I had was something like, I'd draw something like this, but instead of this thing, it would draw here and then make the circle around the wrong side, but only sometimes. If it was, half in one quadrant and half in the other, and so on and so forth, I'd get that problem. And the solution to the problem had to do with something that I discovered, and I wanted to prove a simple theorem about it, and ended up starting this channel. Okay, red and blue are equal by hypothesis. One way to indicate that, actually, I wonder how well this would do as an indicator. It's not very long. If I had two of them together, try it, because I think that's a standard symbol. Two lines through indicates equality. Just so it looks abundantly clear, as much as possible, that the things that are equal here, assumed to be equal, are these colored sides. Alright. Now the theorem states that this is impossible. We cannot form two triangles having such properties. And so assuming that, draw the dotted line. I've drawn it, and the reason for drawing the dotted line is to connect these two vertices. It doesn't have to be horizontal. It just looks horizontal. Then it is clear, it should be clear, that in the red triangle, okay, which is not part of either of our triangles to begin with, but we've just formed a red triangle, that this, since these are the same, and by the last theorem, that makes this an isosceles, that these two angles are the same as this angle because it's an isosceles. So that means this equals this. They don't look very equal, and they're probably not. But anyway, one looks obtuse and one looks acute. Alright, that being the case, since the blue is the sum of two parts, right, this part and this part, and by axiom whatever, 9 or whatever, the whole is greater than the part, then red here being a part of a whole, which is blue, must be less than blue. So red, and I'll use the modern symbol for less than blue, right? Because it's only part of blue. Alright, that's what they've got here. So therefore, adding something, and there is another axiom, unequals added to unequal. No, I don't know about this one. But if I further wish to add to this side, that won't make red any bigger. This side will get bigger. Red is certainly less than the sum of these two parts. In fact, it's less than even part of the sum of these parts. Okay, so duplicate that here. Okay, now since these two blue sides are the same, blue sides, by hypothesis, that means that red is these angles, internal angles, are of an isosceles as before, and so that would imply that red is equal to that, but red equals there, and that's by Theorem 3. Right? And now we've run into a contradiction. So we have a total and absolute absurdity, so which is an absurdity let's see, an insult to the human mind, so vast and all-encompassing, as to render this entire sequence of expressions absurd. We draw the conclusion that the assumption that these two lengths were equal must have been equally absurd. So it follows, certainly in that case, where the line, the vertices line wind up outside, one vertex lies outside of the other triangle. Now at the bottom here, similarly, we have another triad. But what if the vertices don't? What if one vertex lies within the other triangle instead? That's possible. Maybe it's true in that case. This hypothesis still being assumed. The sides are equal in length. The blues equal to the blues, and the reds equal to the reds. Okay. Referring back to the diagram, now they've labeled this blue and yellow. blue and yellow, right, and red and black. That extra bit is because of my little note there. Black, which for me is white. Okay. Now it turns out that the same argument can be applied with this diagram as well. Why? Because of what I've noted here. That the angle red-black, that's this one, red-white I should say, is equal to angle yellow, equal to angle blue here by proposition 4, which states that the external angles of an isosceles when extended, which is the case here, this blue is the external angle of this for this side, and red-blue is the external angle for this side, and they're supposed to, by that problem 4, theorem 3, I guess, or 2, are equal. So this statement is true again. Now, this statement is also still true, because in this blue triangle, what is true? Oh no, sorry. This is true just by examination. Blue is red and white, so red is less than the sum of its parts. Red is a part of blue, so it's less than blue. Okay. Now, red is therefore less than blue plus something else, right? And blue, this here red and blue plus yellow are the interior angles of this isosceles. So therefore they must be equal, just as before. So the same argument follows through in this case, which is a total and absolute absurdity and an insult to anyone's intelligence, and therefore the assumption that it is possible to build such triangles with the same base is false. QED. I guess I got another video out. Okay, so there you go. That's theorem 4 proved. And I hope you like my background. I can always change them. Maybe it looks better here. No, too modern. Or like this scary one. Right. Like that. Or I have another one that's so scary I won't put it in there. How about this? An Asian feel. Although the Asians didn't really develop much in terms of geometry. They did do quite a lot of interesting work on a number of theoretic type problems. Okay, so that's proposition 5. Next proposition, I call this 7. Well, it is 7. This one. Next, proposition 8. If you can see where this is leading, we have now a thing that identifies for us that two known sides and a base identify something unique. That we can't make two things with the same side, with the same 3 sides. An object. Now, see, what we've shown here is not just that we can't make these 2 triangles, right? But we've shown that given a known set of three different sides, this, and this, that uniquely identifies a triangle, because we can't make another one with the same base and these two sides. If we want, we could call this the base and do it from the other side. But either way you put it, it appears as though we succeeded in improving one of the fundamental theorems of geometry. And that fundamental theorem is the basis for why your building isn't falling down and why we can build airplanes and things like that. A triangle is a rigid figure. It cannot be bent or shaped in any other way than it is, because mathematically there is only one solution given three lengths, okay, for a triangle. If you make this thing out of metal, then that's the only thing you can make out of metal with those three sides, and therefore it's rigid and won't disform, and that now has been established. And the next thing that is going to be established has to do with one of the angles of one of these unique things. Okay? I'm sure that this must be appealing to proposition 7 somewhere, but maybe it's just taken. Alright, see you.